All right, the last thing that I'm going to talk about in section 1.6 is something that, to be completely honest, isn't really going to show up on the exam. Now, I know you're probably tempted to go ahead and close the video here, but for anyone that is going to be taking calculus, I really advise you to go ahead and stick with me for just a little bit here. The idea is that we want to talk about what are known as damped trigonometric graphs. If you've never heard of damping before, think about this as almost sort of like a muffling of types. When you provide dampening on something, you might have heard of sound dampening foam. You're basically trying to make it so there's less echo in your room, like if you're recording, which is something I should invest in. But the key idea here is that by looking at a product of two functions, specifically a product of another function and a trig function, we see some unique different results. So here we're going to talk about, in this case, product of two functions. We can look at that by using the properties of the individual functions themselves. The one that they give as an example up front is x times the sine of x. So we're going to look at this as the product of two separate functions, y equals x and y equals sine of x. Then we're going to go ahead and take a look at some different pieces here. One thing that we should keep in mind is that when it comes to our sine function, we know that its range is capped out. It's -1 to 1, which they've summarized using an absolute value expression here. The absolute value of the sine of x is less than or equal to 1. Now, because we're going to be changing the sign, it's going to be going back and forth, even though x is going to increase normally as it goes left to right across our graph, the fact that it's being multiplied by 1 and -1 at different points and swinging back and forth between them is going to cause a very interesting shape to show up. So they're showing their hand a little bit early here. They're mentioning that the product of our x and sine of x, specifically the absolute value of x, times the absolute value of sine of x, is going to be between 0 and the absolute value of x. This is something where they're not being really clear what it means just yet. So I want to go ahead and take it and kind of expand on it piece by piece here. Let's start by getting rid of these absolute value brackets on the inside here, and also this 0 on the left-hand side, since it's not really going to be relevant to us once we remove them. When we go ahead and do that, we end up with this expression instead. We have the opposite of the absolute value of x, guaranteeing that this will be negative, or at least non-positive, is less than or equal to x times the sine of x, which is less than or equal to the absolute value of x. This is really summarized best with this next piece. The graph of x sine of x has to be between two lines. It has to be between y equals x and y equals -x, or the opposite of x. Basically, we're putting a cap on what the outputs of this function can be. They cannot exceed x, and they cannot exceed -x. Sine is always between -1 and 1. So as a result, it's occasionally going to touch the y equals x curve and the y equals -x curve, but it will never go past them. This is something that's really, really important for some work that we do in calculus. Basically, we found a way to squeeze this function between two other ones to give us a better idea of what's going to happen. Now, they've got a little bit more information here, and this is related to what I was talking about a moment ago when I said that we're occasionally going to touch these curves. We know that f of x equal to x times sine of x will take on x and -x as the value whenever sine is +1 or -1 respectively. In other words, this will be at pi over 2 plus an integer multiple of pi. The same thing is going to happen here when we talk about 0. X times sine of x will hit 0 anytime sine would hit 0, which will be any integer multiple of pi. So this is kind of wild, but as we're going forward, we start out at 0. Sine of x is 0, x is 0, we're 0. Boom. When we go to pi over 2, at that moment, sine of x is 1, and x is going to be pi over 2. So we're going to touch when x equals pi over 2 with this curve y equals x. But sometime after that, when we get to pi, all of a sudden we've crashed back down to 0 because sine is going to be 0. And at 3 pi over 2, well, now sine of x is -1. So even though x is 3 pi over 2, because sine is -1, we're going to be down at -3 pi over 2. So we're oscillating back and forth, but unlike our original sine function, which was stuck between -1 and 1, we are stuck between -x and +x. We still have x-intercepts at the same location because of our reliance on sine, And we still have maximums and minimums when we would normally have them for sine and cosine if we were to use that instead. The biggest thing that's going to be different, though, is that our amplitude is changing. Our amplitude is itself a function of x. So as we move further and further away from 0, our amplitude continues to increase. This leads to a very interesting graph. Here we have f of x equals x times the sine of x. The black portion here is, as usual, our graph of the function in question, but the grayed out parts are the part that they were mentioning before. Here is the curve y equals x, and the curve y equals negative x. Our function, x times sine of x, is always stuck between these, but these, however, also act as a sort of amplitude for the function. The further and further we go out from x, the greater and greater our amplitude becomes. So we end up swinging pretty wildly back and forth between these. And so that's kind of the idea of this damping factor here, that x is going to put sort of a limit on what sine of x can go out to. It's going to provide an upper and a lower bound for where this function can hit. And this can be extended to a number of different functions. We're going to take a look at a couple more examples to kind of see it in a little bit more detail. So let's take on this one, for example. The graph of f of x equals x squared times the sine of 3x. There's going to be lots of moving parts here for something like this. First, we want to go ahead and talk about the two different functions that are going to make up this specific function itself. We've got y equals x squared, and we've got y equals sine of 3x. Now we need to talk about how things are going to be bounded. We can see that it's going to follow a similar pattern to what we've already seen, meaning that, in other words, we're going to go ahead and say that this function is going to be bounded by x squared above and below. But we get to make some kind of interesting adjustments. Let's go ahead and break this apart. We've got y equals x squared, and y equals sine of 3x. In this case, that means that we can go ahead and say that x squared times sine of 3x is bounded below by negative x squared and bounded above by positive x squared. I don't need to put absolute values on these because since I'm squaring it first, I know that it'll always be non-negative, so I don't need to have that extra piece here. But these essentially create an upper and lower bound for what the function itself is going to do. Let's talk about the places where we're actually going to hit our curve. When are we actually going to achieve these maximum and minimums? When are we going to run into x squared and negative x squared? So that is based upon our sine function. We're going to ask ourselves basically, when is sine equal to positive or negative 1? Or rather, when is sine of 3x equal to these values? Because we know normally that sine is equal to positive and negative 1 when we're at pi over 2 and 3 pi over 2 respectively. Or rather, any pi over 2 plus n times pi, any integer multiple of pi. So let's do that. 3x equals pi over 2 plus n times pi. This is something we'll do a little bit later when it comes to solving trig equations, but we can preview it a little bit right now. In this case, sine hits positive and negative 1 at any pi over 2 plus an integer multiple of pi. Pi over 2, 3 pi over 2, 5 pi over 2, negative pi over 2, so on and so forth. But since our argument is 3x, that means it's going to happen whenever we're at pi over 6 plus, in this case, this will be n pi over 3. We can talk about how this is going to look specifically just on a segment. So we'll first hit at pi over 6. The next time we hit is going to be at pi over 3 added to this. So you can think about this as pi over 6 and 2 pi over 6. So this will be 3 pi over 6 or pi over 2. The next time will be after we have 2 pi over 3 added to pi over 6. So that'll be at 5 pi over 6. And then this just keeps going. But we're going to be bouncing between. We're going to head up. This is when we hit positive 1. So at this point, we would hit x squared. At this point, we would hit negative 1. So we would bounce to our negative x squared bound. We'd be back up to positive x squared, and so on and so forth. We're constantly bouncing up, down, up, down, up, down. We also are interested in where we're going to have intercepts. So that would be any time that sine of 3x equals 0. And just like before, we can set this up as an argument like this. Sine hits 0 for any n pi where n is an integer. So 3x equals n times pi. So this will happen whenever x is equal to n. I keep wanting to write my n's like pi's. n pi over 3. So it'll happen at just 0, which is when n equals 0. It'll happen at pi over 3. It'll happen at 2 pi over 3, and so on. So I've given us a lot of information here, at least in theory. But let's talk big picture for a moment. Okay. We have our graph here. We know a couple different things about our sine function. We know that it's 0 at 0. That's not so bad. It's going to also have zeros at pi over 3 and 2 pi over 3. Let's go ahead and call this guy out here 2 pi over 3. And then halfway between that will be pi over 3. So we're going to continue to have, in this case, intercepts at those points. But here's where things are different. Normally, for this function, if it was just sine of 3x, at pi over 6, we'd be up at positive 1. But we're not up at positive 1. Instead, we're up at x squared. And x in this case is pi over 6, meaning that here, in between these two values, at pi over 6, our actual output for the function, since sine will be 1, is equal to x squared, or what will be pi squared over 36. A little bit unusual, all things considered, and this is going to continue to happen here. At pi over 2, we're going to actually be hitting negative x squared, where x is again pi over 2. So this will be negative pi squared over 4. Where are we going to land when x is 5 pi over 6? Well, sine is going to output 1. So x squared is actually going to be in the driver's seat. So this will be 25 pi squared over 36. So our outputs aren't 1 and negative 1 anymore. That's the output for sine, sure, but because we have this damping factor, it's going to add an extra layer of complexity to the work that we're doing here. And so that's going to give us a very different shape for the final piece of our graph when we take a look at it. Let me go ahead and pull it up real quick so that you guys can see what it looks like all told. So here, this is what it looks like after we actually sketch it. And you'll see the grayed out portions again represent our upper and lower bounds, y equals x squared and y equals negative x squared. So we're constantly bouncing between those two different values to go ahead and sketch our curve. It's a little bit more complicated, but this is going to be one of the most important things we do in a certain portion of calculus. There's a very interesting function that we want to talk about, and that is the function where it's sine of x over x. It has lots of implications for other parts of calculus, and so we're interested in what happens at sine of x over x as x gets closer and closer to 0. Because something interesting happens, and it's a result that leads to a lot of different takeaways in early parts of derivatives for trig functions. Again, if you don't have to see calculus, you don't really have to worry about it too much, but I want you to kind of start seeing the picture for yourself. All right, that's going to do it for Lecture 10. The remaining slides are summaries of the 6 trig functions and their graphs, a great place to study as you guys prepare for Exam 2.